So we should be on live. Yeah, it's coming up. So we have around. Okay, so we just have 1 more minute and then we'll get going.
So if I open the YouTube, this thing, I should be able to see the comments myself, right? The same way.
Yeah, you should be able to see that. Yes, if there are any comments, but I'll be posting them here.
Sure. Okay, I don't
Okay, so I
know.
think it's already live now.
Cool.
So, hey everyone, thanks for joining in for this event. Um, so, this event, let me just share my screen. So, as in this event, we are going to cover ePBF and Cube Armor. So, I'm going to cover the topic of ePBF, and Rahul will take over the topic of Cube Armor post that. So, I'll go first with the ePBF topic, and then we'll have Rahul to cover the things. Thanks you for joining in. And this event, I think we are doing almost, I mean, 10 or 11th months. We did the last event in Jan, but last year we have been very active. And I believe that we'll continue this in the next coming year to share the knowledge, to learn from everybody. Yeah, so that's the kind of expectation. That's the thing which we'll plan to do the next year. So before, without taking any time, let's kind of dive into the topic of ePBF now. So let me just put that topic in here. Yeah. So I'm not going to share any slide per se. What I have done is I have prepared a blog. So if you go to our Cloudika's website, and you can actually perform these steps as I'm doing there. So we have the concept of hands-on lab, and you should be able to, if you want to kind of do the hands-on lab with me, you can do that as you would want to. So like I'm going to kind of click on this hands-on lab here. You can also do it as well. So I'm going to trigger the lab setup here. This takes around 80 seconds. So let it happen behind the scene. Meanwhile, we'll kind of go over with the concept of ePBF uh, and do that. So let me just remove this panel here. Okay. Oops. Okay. Fine. I'm just okay. So let's go over with the topic of ePBF. So just want to kind of understand how many of you have tried compiling a Linux kernel earlier. Have you got a chance to kind of build a feature on Linux and see how long it takes to build a feature on Linux and get it live in the upstream, right? That kind of have been very challenging over the years, and nobody want to kind of wait for that long to have their feature in place. Uh, so that's where this technology of ePBF primarily comes handy, and this is kind of changing the way JavaScript helped us to kind of deploy or build these web apps on the browser, right? So we can now see our kind of as a presentations, sheets, or whatever, right? Mail and everything on the browser now. So the way JavaScript changed that stuff, similar thing we expect that ePBF is going to change in the system side. So now lab setup is being done here. So I'm just going to bring this down for a while here. I'll tell you what happening. But so lab is being done, so we can do hands-on lab on that as we continue. So let's look at the kind of a background of BPBF before we jump into ePBF. So BPF is basically Berkeley packet filter, and that has been primarily built to basically uh, kind of whatever the network packets we have, I want to filter them. I want to find out more information about it. So that's what it's been built for. So as you can see on the screen, in any OS, we have a user space and the kernel space, right? And if you do any operation, for example, if a packet comes over the network and you want to analyze it, and if you analyze it on the user space, it's going to be very expensive, correct? But if you analyze them in the network, it's going to be much better there. So that is what the VPF was built for, that we can analyze these packets on the kernel space. That would be much more faster, and that's what BPF kind of came into picture. So it was implemented as a virtual machine. So it's like you are having a Linux kernel, and inside that you create a virtual machine that is being built for a specific purpose to filter the packets for you. And that was basically inside the kernel, but it's like a kernel module there. So basically, it kept a distance from the Linux kernel, but still it was trying to make things faster for you. So that was what BPBF has been there for a while. And if you have used TCP dump, I'm pretty sure all of you would have used TCP dump. TCP dump used BPF to kind of combine or take that feature to analyze the network packets, and whatever the UI you get with this what do you call, say, with the next TCP dump, it was due to this particular BPF filtering there. Now let's talk about, just give me a minute. So now let's talk about what is EPBF, right? As the name suggests, is it Extended Berkeley Packet Filter? That is what its name suggests. So it was kind of got into the Linux kernel in kernel 3.18, and it was implemented using the BPF system call. It is more efficient than the classic BPF, and it was implemented not just for the network. Now it can do more thing. It's like a general event processing thing. So it was not just made for network, but for other stuff as well. So we'll talk about what those other stuffs are. And it also has a concept of maps, using which basically we can share the content. So basically we can collect the data. So what's happening in this case is, in EPBF, again, you have a virtual machine concept. With the help of that particular virtual machine, we can collect the data, but that data basically get back to the user space with the help of maps. So these maps are basically being built specifically to have that communication going back and forth. So EPBF basically can extend the functionality of Linux on the fly. So you don't need to kind of write any kernel code or load any modules there. You can just basically instrument, or you can put anything in the Linux kernel by just writing this particular program, and this basically takes everything to the next level, right? For example, if I talk about, you can put probes, or you can basically look at what you call. So you can attach this program of EPBF into any kernel function, correct? You can put them into any user space functions. You can do for network cards, any trace points, any USTD kind of tracing points there. So if you can kind of combine all of these things, you get a very powerful system using which you can basically do different stuff in terms of security, tracing and profiling, networking, and observability and monitoring space there. So if I talk about the example of security, like I think Falco is built on EPBF, right? It kind of uses that one. Similarly, I believe with the app, the Cube Armor, we'll see that some of the use cases there as well. We can trace and profile any kernel function, any programs, what we have there, and we'll see with the example, with the help of example. Networking, which is basically like, if you talk about Cilium, right? So Cilium is using this EPBF to kind of do all the CNI stuff, what you typically do in Kubernetes, right? You send packets between pods and network and different nodes and so on. So with the help of EPBF, Cilium is getting lot of performance benefit. That maybe we'll cover in some other event, but this is kind of primarily focusing on the basics of the technology here. So let's look at some examples before we kind of even talk about anything. So we are going to use this thing called BPF trace package, using which we can put the traces on different stuff in a very easier way. So let me show you that. So what we'll do is we are going to install this package here. So what happened is, as we trigger the lab, a kind of VM get triggered behind the scene, and I can interact with this VM as I would do it, or I can basically run any commands like this here. So I'm going to run a command here. This is going to run the command again, the same infra what we have. And once it's been done, we would see that it's going to install that particular package. And let's let it happen. Yeah, so this kind of package got installed on the environment here. And now what I'll do is I'm just going to use tmux here to partition the my terminal here. Now what I'm going to do is I'm going to put a kind of I want to use this BPF trace, and I want to put a figure out how many system calls where what happens till the time I'm going to run this particular program. And what I'm doing now is I attached a kind of a say trace or probe into the sys enter. So basically any system call happening, I would be able to trace it, right? So for example, if I come here and now perform anything, any commands here, whatever commands I'm doing, and if I kind of go back, let it just happen. Connect, yeah. I think it just got into tmux attach. Just a minute. Yeah. So now I'm going to kind of go there. So I run cal command. I'll go here on the other terminal and basically do a yeah. Yeah, so I'll do a cancel. Yes, as you can see here, the system calls have been called by this. So in between, whenever this probe has been running, in between all of these system calls has been called from our system. Correct. Now let's say I want to put another um, example here. So now I want to kind of find out what are the bash commands have been running around in all my systems. So I run this particular program of EPBF again. And now whatever commands you would run, whichever terminal, right? All of those commands would be shown here. So for example, if I type date command here, right? So that should have been coming there. So as you can see now, the cal command which I ran is there, right? If I run the ls command here, if I open or a cat command, as you can see that whatever commands I'm running in the entire system, these are getting traced, which is like very powerful for me, right? If I'm a admin or I'm doing anything kind of debugging, if I can figure out run these kind of things and see what's happening, right? This is kind of very good data for me to do anything. Or kind of figure out internals. And the next thing now we want to do is I want to trace for all the new programs with the exec call. So I'm just going to again this another program with this BPF trace here. So now again, if I kind of come here and do any of the program here, let me do that. So for example, if I do, let's say cat slash etcos release file, it's kind of telling me what PIDs has triggered this. If I look at here, so yeah, so it's kind of telling me the PIDs and so whenever an exec call is being called, I'm getting that information there. Let's look at the next one here. Now I'm going to figure out the information about the TCP connections. So I'm going to run another function here, another program, and I want to now figure out what you call say the TCP connections, what's happening from where and all that stuff, right? Within this one single thing. So I'm again going to kind of perform some operations here. Let's say I do apt update now. And you can see that it is telling me about all the connections which is being made, all the TCP connections which is being made in between, right? So this is kind of just by single stuff, you can kind of collect all the information with EPBF, right? So again, these things are nothing but these are putting different probes behind the scene. So let me see if I can show you. I'm not sure whether these programs are binary or what are they. So let me just see that. So cat USR has been TCP connect. Yeah, so you can see that again, these are some helper function being written with the help of ePBF. And I'll tell you how this is being, this is a K probe, as you can see here. It's putting a K probe on the TCP connect, right? So ePBF, with the help of ePBF, we are kind of inserting this stuff on the fly inside our kernel. And now I'm kind of tracing all the TCP connect, correct? So this kind of things, what I can do very easily. So it's kind of ideas to kind of give you a very high level overview what is possible with ePBF. Now we'll look at the underlying working and how it is happening behind the scenes. So let's talk about that now. Okay, before we dive into that, this is the BPF trace probe type. So as you can see on the screen, you can put these probes anywhere, right? Be it in the user space, be in the kernel space, everywhere you can apply these kind of the traces, and this is going to give you a way lot of information which have been not possible by just the normal tools which you have been using, right? So let's see if there are any comments on the screen now. So okay, so question is how EP relates to Kubernetes, right? So as you know, right, you are running Kubernetes on Linux, right? And you want to basically you want to collect the performance data everywhere, right? Of be it from the node perspective, be it from the traffic perspective. The other example, what Abhijit said about Calico, not Calico, like Cilium, right? So yeah, I think Rahul already answered that, but because you are working in the system side, right? And as you can see here, wherever you can see, you can put probes at different places. So like if you heard about Falco, right? Falco is giving you the security. So what it I think it's runtime security feature, right? So you can use get runtime features, runtime security information uh, by the Falco, which is implemented behind the scene by ePBF. And I think Rahul would talk further on this, right? So let's talk about how does the ePBF programs work in general, right? First of all, when you want to put ePBF programs inside the kernel, we have to generate some kind of a bytecode, and that bytecode is being used by the underlying kernel to insert your functions or information, insert your request natively on the kernel there. So what's happening here is we basically need to kind of generate this bytecode. So this we can generate, like as you can say that you can write a manual program. Either you can just write from the manually from object file, right? You can build all this stuff as well. But there are some helper functions that are available, like the way which we saw earlier, that playground program for TCP connect stuff, right? So we need to kind of have this bytecode generated in the user space, and that bytecode we are sending into the kernel space using the BPF system call. The system call is so that implemented some time back. So with that system call, we can send this bytecode. That bytecode first reaches to the verifier. So verifier is something which is going to check whether whatever code you are inserting in the kernel is it secure or is secure, and in a way it is not going to make any harm to the kernel which is running. So like there is no infinite for loop, there's no memory leak and all that stuff. So that need to be checked. Post that, we have something called as just-in-time compiler. This bytecode is a very generic code which you have written, but then depending on the underlying infra what you have, architecture what you have, right? Like you are on which architecture, x86 and so on. Depending on that, basically we do just-in-time compilation, and then that particular get inserted into your kernel. So that as a kind of virtual machine there, that virtual machine is going to be running in your along with the kernel, and post that what will happen is we are going to attach that functionality whatever we have done, whatever say we said we want to apply for this function. So I want to probe, I want to put the what you call say, let's say I'm putting some tracing there. I want to have a trace at a given kernel function there. Now post that, okay, maybe let me just take my step back. Once basically our code is compiled, become part of the kernel, then we are going to attach to different events. So for example, if I have said that, okay, I want to attach to every kernel function which is going in and out, right? I want to attach to every network packet. So that way, the BPBF function is going to be attached to the given event, what you are saying. And once the event has occurred, we are going to collect the data, whatever data is need to be collected. Like, for example, I want to find out when the TCP packet comes up, what is source, destination, and all that stuff. So all that information basically does not get stored in this VM. We have a concept of maps, as I said earlier. So now what we can do is, as the data we have got it, we'll put in the maps, and then these maps basically would be read by the user space program. So like the way we saw in the terminal, that's what's happening there. So when the function occurred, right, when the TCP connection occurred, we called all that information. That information got into the maps, and from the user space program, we can see that information on our terminal there. Okay, so that is how the this ePBF is working there. So let's talk about a few more stuff here. So I talked about bytecode earlier, right? So those bytecodes you can generate by different front ends. Front end means like which are supporting functions for you, using which. Um, mm, uh, okay, so there was one question here. Let me take that first. So does ePBF needs to run at the root level to listen the kernel space? Yes, of course. You need to have the right permission. So as this particular things need to become part of kernel. So as you are running this program of ePBF, when you kind of insert this bytecode, you need to have the right privilege so that this particular thing goes inside the kernel. You cannot run as a normal user which doesn't have permission. So you need to make this as a part of the kernel. So you need to have a permission there to make it that happen. Okay. So I think that's there. So I was talking about some of these front ends, right? So let me just kind of go a bit down here. So there are different front ends are available using which you can build these. You can build these bytecode very easily. So like there is libraries in C++. There is a tool called BCC, BPF trace, ePBF Go libraries. There are different libraries are available using which you can easily build these bytecodes. And I'm going to show the example to you just after this. To talk about different kind of maps here. So these maps, what I said earlier, right? These maps, these can be hash tables, LRUs, ring buffers. There are different kind of maps are there, which are efficiently going to have you share the content from the kernel space to the user space so that we can easily get them on the user space and then do something about that, right? The similar diagram as earlier, but we just added the front end. So with this front end, we can easily build these bytecodes. So I'm going to give an example of what you call say the Python based program using which we can write our own ePBF based program and then see how it is going to work. So for that purpose, we need to install this package, which is going to bring me that Python library. So I'm just going to install this particular packages here. I said that you can do it simultaneously with me as I'm doing that. On our website, you can do that. So now it's been installed. Now here is the basic Python program which is there. So what's happening here is I'm kind of using this BCC module to import the BPBF. So basically, we are importing this BPBF function here. You can say that. Now here we are writing a program. So define the BPBF program. Again, this example has been taken from the BCC website. You can check them out, more details there. So here we are saying that there is a function we are writing program, and we are putting this function here in which what we are saying is have the BPF trace print k function. So you're writing a hello function, and every time whenever we attach to the function which okay, so we are going to write this program called hello, which basically prints hello KTS and cloud native community every time we hit our function which we are attaching to, right? So we have written this particular program here. Then what we are doing is we are loading that program into the kernel by this BPBF program, the function there. So this is going to basically take your the byte level code base. It is going to verify and just in time compile it. So that step happened here. And then we are putting this particular function the hello function with all the clone system call. So whenever system call clone is being called, so basically whenever we're creating a new program, every time the hello function will also be called, right? So we are going to load this program at the time of whenever the clone system call is called. Then what's happening next is we are going to put down the header perfectly fine. Now I'm running a while loop here. So every time we clone something, we are going to get this output of hello KTest community and all that. So I'm just going to run this program now. So let me just go ahead and do that. This program is now running. Okay, let me just trigger it into Tmux thing. It's been running. As you can see that whatever I'm doing, right, at which time I'll do something, it's going to print that stuff, right? So if whatever, I mean, I do anything, I'm just going to clone something, right? And whenever I clone, it is going to give me that output. This is how we can have our own BPF kind of program attached to the kernel on a given system call or a given event. That's going to be attached there, right? So, and you can find many other examples on the site of bpvf.io, and there is this GitHub IO Visor here. So here you would find way too many examples which I have just shown here. So you can come down here, and then there are examples of trace events, dump Unix socket packets, and everything. So you can just kind of install that package, and you can start finding out these insights about your system, correct? Which is, I mean, just I believe just way too better than doing anything else. So whatever the tools have been there in the system side for performance monitoring and so on, they're kind of getting obsolete because of the ePBF kind of implementation. And even people are now saying that ePBF is going to be the technology using which we'll rewrite entire kernel perspective there. So I think it's very interesting thing, and very interesting ahead what we are going to see with the help of ePBF there. Okay, so that's all from my side perspective. Any questions you have? I know that Rahul has already answered some of them. Yeah, so yep. So any questions, please make them on the chat here if you have any questions right now. Otherwise, I said that right earlier, you can go ahead and try out this particular lab on our site if you would wish to. So you just need to go to clouddigger.guru and go to hands-on labs. And then you will find this example, and then you can try out on your own. Yeah. Any more questions? I'll just wait for a minute. Hey Rahul, so how was it like? What do you think that? Anything you want to add on further on this?
Brilliant. Nipendra, thank you for that introduction. In fact, I know a few notable points that I have. I really like the hands-on labs,
Okay.
mechanism that you have. It really is very easy to use and very easy to demo things. I wish I could have prepared something like this for myself.
Mm-hmm.
Second part is usually I get this question out there. eBPF is a Linux technology. What about other platforms? And this comes from a lot of customers with whom we work with. But there is a good news that eBPF is soon coming to Windows as well. A lot of you might have already know about it. Dave Thaler's team from Microsoft is working on bringing eBPF to Windows. It remains to be seen as to what all kernel hooks, what all the power of eBPF lies in what all kernel hooks it support, right? And the flexibility of the bytecode that Windows has to deal with itself. But in the long run, if there is a compatible bytecode and compatible LS hooks that we find in Linux and Windows kernel, we'll be able to use the same eBPF code regardless of the platform, and that would be brilliant. That would change the whole arena of what eBPF can do today and versus tomorrow.
Yeah, for sure. That's like future is really good, in this technology. So Vijay has one question there. Will eBPF replace qProxy? Yes, there is, and Cilium does that actually. So if you use Cilium and if you want to replace qProxy, you can do that, and that makes a significant performance improvement. So there is a talk from someone from the EPF community, I think Thomas. You can check out that particular presentation of his, and you really find okay how he's talking about how we can replace qProxy with ePBF, and so complete the IP tables I think can go away, and you would make your network packets go at a very lightning speed there. So yeah, I think that's possible for sure, Vijay. And just look for that presentations. And I think some in KubeCon also we talked about a complete event is in that, right? If you talk about KubeCon conference, there's a video replacing Kube proxy. I think there's a talk like that. So just you might be able to get it.
Indeed, and that's a brilliant question again. As we can see already, some of the primitives technologies that we have been using since past 20-25 years have been slowly replaced. Essentially, IP tables getting replaced by eBPF. The kind of performance gains it adds for a CNI is immense. In place of anyone who has worked with IP tables, if you are working with IP table rules to the tune of 100 rules, if you are adding 101 rules or 1,000 rules, which is what is required in a practical Kubernetes environment, you'll soon run into scale issues.
Yeah.
With eBPF, you will be able to handle the scale issues, and Cilium does a brilliant job about using identity with combined with eBPF to handle that problem. It's just a brilliant way of handling things. Yeah.
So there's a question: how easy to replace? It is up to upgrade the qProxy to eBPF model. I think if you use a Cilium thing, it would be kind of done automatically, if I'm not wrong, right? So if you just use the Cilium as a driver for a CNI plugin for a Kubernetes, I think it's out of the box. Even maybe some configuration would be required there, but the only condition is you have to use the Cilium as a CNI plugin there.
Correct. I would like to just apprise of one more development in the context. There was a work that was initiated by Red Hat to replace IP tables backend with eBPF based backend, regardless of Kubernetes or no, Kubernetes or regardless of the Kubernetes orchestration system. However, that work has not finished. I believe Florian Westphal, again, our engineer, superb engineer from Red Hat, was working on it. He presented it in few of the NetDev conferences, but I'm not sure of its current status. That is a work. If that works get done, essentially we'll be able to use the same IP table front end, same way of specifying the rules, but in the backend it will use eBPF. So that is another model to work with. But again, it remains to be seen as to how much that can be done and how much can be upstream in the Linux kernel.
Okay. Yep. Okay, I'll try to find the presentation, Vijay, and give it to you before the session ends. So I think that's all from my side, and we can take questions as they come in. But I think now Rahul can take over and talk about KubeArmor.
Thank you, Nipendra.
Share my presentation. Yeah, go ahead, Rahul.
Okay, let me share my screen. Okay, I hope I'm sharing my right screen. Are we there, Nipendra? Since I can't figure out if it is shared or not. So, okay, all right. So I believe the screen is shared. Before going into the details, I would like to give some background about myself, Aquinox, which is a company sponsoring KubeArmor as a project, and what in a gist is KubeArmor, a TLDR like statement for KubeArmor. So I'm Rahul Jadhav. I've been a kernel developer. I've been working with Huawei for past 11 years in the domain of network and transport optimization for past 20 years. eBPF came as a sweet surprise for me when I was working on a multipath tunnel project in Huawei, where we had to basically drive the packets to the right core. So with multi-part transports, you need to drive the packets to the right core, and eBPF was the right tool for us that eventually helped us to do that mapping of packets from one core to another right in the kernel space without having to move it into user space. There are a lot of use cases that you'll see in context of eBPF. What we are doing in Aquinox is that we are working on something called as runtime security. Of course, most of you already are aware of runtime security. We are using KubeArmor as a way to use it as a runtime, application security for Kubernetes containers, and in the future, we'll even we have already started work to extend that to bare metal and virtual machine based workloads as well. So thank you for giving this opportunity to talk here. And meanwhile, one good news I wanted to share is, just last week, KubeArmor was formally included as a CNCF sandbox project, which means that we'll be following all the CNCF governance methodologies, maintainers. We will have a technical steering committee to handle all the changes, upstreaming activities, and all that. We would highly welcome anyone who would like to contribute towards open source in CNCF. We are very active on Slack, and we are looking forward to having contributors from external organizations or anyone who just wants to try out KubeArmor and contribute towards anything in CNCF. So with that said, let me go on to the next aspect. The primary problem that we were solving is, when we started working in Aquinox, we wanted a system which can protect the containers. We were focused on runtime security. Runtime security has three aspects, right? How do you protect the communication between multiple pods? How do you make sure that the pods internally within the pods, multiple containers within the pod, are doing what they are intended to do? And the third is, how is the data security handled? Like, if someone tries to exfiltrate the data, how would you know about it? How would you protect that? So these are the three runtime security things that Aquinox as an organization is concentrating on, and KubeArmor is basically focusing on systems and applications protection. We are also an active contributor to Cilium, which we are using for network protection, and the data security is something that we are developing in-house. It's not open sourced as yet. But KubeArmor has been open sourced in its fullest form right from day one. We had always wanted to go back to CNCF because of the model that they have, the free governance model that they have, and really appreciate all the feedback and support that we have got from the community all these years, so as to make CNCF make KubeArmor part of CNCF sandbox. So the problem that we are trying to solve is, we want to protect pods, the activities of the pod. Most of you might have heard of AppArmor and SELinux in the context of Linux. These are essentially Linux security modules, which allows you to protect the host operating system or the host activities of a particular application. For example, for SELinux, for Apache NGINX, you get predefined SELinux profiles, which will say that NGINX should do only this and this. Apache should do only this and this. All this worked at the host level. What KubeArmor is trying to do is it's trying to bring this notion of protection to the pod level. So essentially, SELinux, AppArmor, and the future primitives that are built as part of Linux LSMs are being brought to KubeArmor. What KubeArmor does is it internally uses AppArmor, SELinux, BPF LSM, or any other Linux security module to enforce the application security. Now, one problem that typically we had been having, or our customers have been having, is why not directly? So the question usually comes up: why we can directly use SELinux, right, today, or AppArmor? What is stopping us from allowing us to use that in the context of pod? Well, the primary problem is, the SELinux and AppArmor is extremely difficult to configure, get it right in the first place. Anyone who has worked with SELinux, in fact, there's a quote in SELinux that whenever an administrator comes against a SELinux setup or a flag, the first thing that they do is turn off SLNX because it's so damn hard to configure in the first place. With KubeArmor, we want to hide the deployment complexity of AppArmor, SLNX, other LSMs using a declarative YAML specification of Kubernetes. I'll show you an examples for that. Again, there's one more thing that is mentioned here, MITRE TTPs. MITRE is an attack framework. TTPs are tactics, techniques, and procedures. MITRE framework explains what are the different tactics, techniques, and procedures an attacker will make use of to get into your system. And KubeArmor started dealing with these tactics, techniques, and procedures when during the beginning of we started making use of Falco, Tracy, and other engines out there, and very soon realized that some of the use cases cannot be satisfied, and I'll go into some of the use cases in the subsequent slide, with existing runtime security engines. That's why we started building on KubeArmor. KubeArmor is a year and a half old. Again, it's still a budding project. That's why it is in CLCF sandbox as of now. Okay, so like I said, what the solution KubeArmor in a gist is that KubeArmor leverages LSMs, Linux security modules. In simple words, AppArmor, SLNX, Tomoyo, SMAC, these are different LSMs that are available with Linux today. Remember that SLNX and AppArmor cannot be used together, which means that either AppArmor will be available on a given system or SLNX will be available on a given system. And what we found is that in general, the cloud providers are divided on what to go with. For example, GKE COS, container optimized system, container optimized OS, goes with AppArmor as the default LSM engine, while BottleRocket, EKS, Amazon Linux 2, they by default make use of SLNX. So in a way, what I'm trying to say is, if anyone wants to get into the application security using native LSM constructs, they'll have to learn both AppArmor as well as SLNX, and then find a way of orchestrating these policies against the pods. It's very difficult to handle. What do we have today in Kubernetes? What we have today is pod security context, and I'm sure most of you might have already used pod security context. So pod security context is essentially an admission controller. Pod security policies is essentially an admission controller. KubeArmor and pod security policies are essentially complementary. There is also something called as pod security context, but pod security context basically expects the user to understand SLNX and AppArmor policy constructs. The language that SLNX and AppArmor use, that is what they expect you to understand, and then specify that the context of SLNX policy in the context of pod security context. In general, a deployment can have a mix of both SLNX and AppArmor, in which case, like I mentioned, an administrator, DevSecOps team has to understand both these primitives in its native form. With KubeArmor, we are essentially abstracting that layer and making it easier for users to deploy LSM. So that is our primary proposition with KubeArmor. The other aspect with KubeArmor is visibility and observability. So what has to be done? What processes have to be spawned, or what processes have to be should not be allowed to be spawned? What file system accesses should be allowed by a pod to be made? All this requires you to have a visibility engine in the first place. So KubeArmor has two propositions. One is it has a visibility engine, which means that if you set annotations in the context of your pods, it will show you what are all the different paths it is accessing, what are the different processes it is spawning, what are the different capabilities it is making use of, what are the different syscalls it is making use of. And so that can be used subsequently for policy definition, KubeArmor policy definition. Below in the light green color box, it's shown as to what all things you can do with KubeArmor today. You can limit attacker within the pod, limit what processes are allowed to be spawned in that pod, what file system accesses are allowed by the processes. So you can say that NGINX process is allowed to access this particular file path. No other process in the same pod or container would be allowed to access the same path. You can be as that detailed. You can limit the capabilities of the container. I don't think limiting the capability of a container is a new proposition here, because already pod security context and pod security policies in a way allow you to do that. But what KubeArmor allows you to do is it allows you to do that dynamically. Means while the pod is operational, you can change the set of capabilities, which means that in the initialization state of the pod, you can set different capabilities. And once the pod, you can say after 20 seconds or after 1 minute, you set these capabilities. What we have seen usually is that when a process starts in the initialization and the cleanup state, a different set of capabilities are used, while in the running phase, a different set of capabilities are used. So essentially, KubeArmor will allow you to change the capabilities at runtime. So so this slide basically talks about what are the different MITRE tactics and techniques which are addressed by KubeArmor today. One good learning that we had was, today whenever anyone thinks about runtime security, the first thing that comes to anyone's mind is, how do you protect the network? How do you protect the communication primitives? In general, what we found with MITRE is that there are more number of systems and application controls or application tactics for an attacker than the network communication. Today, the attacker can get into your system, not necessarily through a network-based attack, but it could be a supply chain attack. It could be, the container that you're using could be compromised by itself. So you have to take into consideration these attacks as well. So just relying on network-based security is not a good idea. Of course, you have to do network-based security as well. If you have to cover both all three things: network, systems, and data. But what I'm trying to say is, in case of MITRE, you'll see most of the controls, most of the tactics and techniques are in the context of systems and applications. And there are existing solutions. Falco's name came up multiple times during the eBPF session from Deepinder. And Tracy is another brilliant engine out there. And they do a fantastic job about integrating eBPF-based backend and couples it with Kubernetes metadata to provide flexible rule engine with immediate alerts. You can say, if this system call is executed and these are the parameters of the system call, then you send an alert with this severity, with this message, with these tags and all that information. It's an extremely flexible engine. But at the end of the day, Falco and Tracy are both auditing engines, which means that they cannot enforce a setting. Let me give an example here. If an attacker comes into the pod and tries to unlink a file, unlink a security or a sensitive file or a sensitive data store, you can get an alert using Falco and Tracy. But since KubeArmor integrates with Linux LSMs, KubeArmor can essentially do inline security controls, which means that before the file is deleted, it will send out saying that this action was blocked. And we found that there are a lot of rules that one can just come up saying that, there is no reason why a pod or a process should have access to these sensitive paths, or only a particular process needs to access these sensitive paths. If you have a MySQL process, only MySQL is the process we should be only MySQL is the process we should be allowed to access the data stores which MySQL creates. No one else should be allowed to access that, right? Simple statements like that. So having an enforcement engine is what we work towards, and that is what sets us apart from Falco and Tracy. Now, the other aspect is, what about auditing? So you cannot have enforcement without auditing had been our mantra from day one. We have to do auditing as well. So we allow auditing of the events and then allowing the user to block in the subsequent stage. That's up to the user as to do. The user can keep the policies in audit mode, check its impact on the applications, and then convert that audit mode into a block mode, which means that if you have so if your application depends upon some access which the policy is going to deny, you will come to know beforehand. So there are different terms used in this context: dry run, auditing, these are some of the terms that are used in the same context. So what I'm trying to say is CubeArmor is both an auditing as well as enforcement engine. Now, let me quickly go into the system's primitives. So when it comes to doing runtime enforcement, what are the different options available with Linux kernel and Linux OS in general? One is, of course, the Linux security modules. There's AppArmor, SELinux, SMAC, Tomoyo, and so on. There's several LSMs. I know I might have forgot to add your favorite LSM here, but there's so many of them. BPF LSM is a new work, and I'll talk about it in a separate slide in the coming few slides. KRSI was the previous name for BPF LSM, Kernel Runtime Security Instrument. This work was started by Google. KP Singh was the lead author, is the lead author for this work. The use case that Google targeted was very different. They wanted to protect Chrome browser from Chrome has these extensions, right? They wanted to protect these extensions from accessing, doing unwanted accesses, they prevent from doing unwanted accesses. So that is what their use case was. The same use case now a lot of folks are extending towards Kubernetes, but it will require its own time to mature. But this is a very new, interesting development that is happening. LSM doesn't suffer from the problem of time to check versus time to use. Like in the case of Falco, you can argue that once you get an audit event from the user space, you can go and kill the process. But by the time you kill the process, the sensitive data store might have been already deleted or tampered with. So time to check versus time to use. If you have an inline security control based on LSM, it would be able to block the access at runtime without having to go through the user space or through other policy monitoring system. But the problem is it requires Kubernetes and Docker. LSMs are not integrated with Kubernetes and Docker, and that is where CubeArmor comes into picture. There's a steep learning curve for policy language. Anyone who has worked on SELinux, AppArmor is relatively easy, is what we feel. But each engine has its own flexibility, and it's extremely difficult to get it right in the first place. Even if you end up learning these policy construct languages, it's extremely difficult to get it right because of multi-level hierarchy of labels and type enforcements and things like that in SELinux. And to make it worse, the different LSM, there were different versions of LSMs. Like AppArmor, there's the version 1, 2, and 3. They all behave differently. They all provide different protections. As an administrator, as a DevSecOps person, or as a DevOps person, or as a developer as well, you won't be able to catch up with all these. Or you may be able to catch up, but it will take a significant time. Another aspect, another primitive here is seccomp. Seccomp allows you to basically seccomp allows you to sandbox a given Docker. You can specify a seccomp profile when starting a pod in the Docker. During the start of container, you can specify the seccomp profile it uses. That seccomp profile essentially limits what system calls that container can use. Essentially, limiting the system calls limits the ability for that container to call those system calls. For example, you can specify unlink as a system call which is denied, and then no one would be able to use unlink or delete the files in that container. Again, there are a few problems with seccomp. One is seccomp is a one-way transition to restricted state. Means once you set a container in that particular mode, you can't change that setting at runtime. Meaning that if you say I want to restrict system call 1, 2, and 3, then at runtime, you can't say that I want to now allow system call 2, or I want to now add system call 4 as well to the restricted list. That you can't do. It's a one-way transition to restricted state. That also means that you can't do dynamic enforcement. You can't change the system call list at runtime. I would limited. It has seen limited adoption till date. Again, that's my observation. I would be happy to prove wrong. If anyone of you have already made use of seccomp in production environment, I would love to know and discuss more about it. In fact, that would be a great topic of conversation on CubeArmor Slack. And then there are user space controls, like, this topic also comes up very frequently. You have LD preload, wherein you can intercept the library calls and then return whatever you want. If someone calls up fopen, then you can return EPERM and deny a fopen call based on the parameters that. But the primary problem with LD preload, as anyone who had used LD preload, is that it hooks into library calls. There are ways in which the user can directly call system calls bypassing the library calls altogether. Again, I know there are few enforcement engines out there, not open source, but proprietary enforcement engines out there which is using this LD preload technique. But this technique provides you a very good flexibility right in the user space itself, but it's not good enough. Most of the attackers are shrewd enough or smart enough to make use of to directly call the system calls bypassing the library calls. No one would take that risk. No attacker will take that risk. Okay, and one more problem is with Golang. Most of the microservices are built on Golang. Golang mostly builds, it links statically almost all the libraries, so you don't have dependencies like you used to have in the traditional world. And now I coded for 20 years in C. Golang was a different world altogether. But some of the decisions that Golang got right is that they don't keep lot of dependent libraries. So you have a single self-composed, self-contained binary which is statically linked, and you're good to go by copying that binary anywhere. So in that case, LD preload can't work. Now this is an example slide which talks about asynchronous control, which essentially you can do with Falco and Tracy, and then there is inline control here. So with asynchronous control, you have malicious process trying to do a file open of sensitive file. The kernel primitives of Falco and Tracy could potentially understand that this is a sensitive file, and someone is trying to fopen, then send an alert. Then audit and alert handler will send it to the policy engine. Policy engine might end up killing the process. All good here, but the problem is by the time the process is killed, this action, you cannot stop this action from happening. You can send an alert, but so that is where inline control essentially helps. So LSM hooks basically operate in this manner. You have LSM hooks built right into the kernel, and there is a policy engine. This policy engine is essentially either SLinux or AppArmor or any of the LSMs. In the future, we can add BPF bytecode here as well on the LSM hooks and tell what to do, what not to do at runtime, essentially providing you an inline control. That is what we mean by true runtime enforcement. This in a nutshell is what KubeArmor looks like today, and the high level architecture for KubeArmor. We have Kubernetes, which is orchestrating all the policies. The user specified policy goes to KubeArmor. This is a YAML file, so user is only concerned about the YAML file. KubeArmor internally checks what is the deployment. Is it making use of AppArmor or SLinux? Then picks up one of the appropriate LSM here, and then uses that, converts that YAML into appropriate language here, and then enforces those system controls. The eBPF part here is used for auditing purpose, which means that if there is any system call which gets rejected, we have an eBPF handler to identify what got rejected and then send out an alert based on that. So eBPF helps us to identify the kernel events and then attach Kubernetes metadata, namespace, container ID, Docker information in the context of that alert, and then send it out to the whatever your SIAM integration would look like, Elastic or Splunk or things like that. The same is applicable for visibility as well. For visibility, we just make use of KubeArmor with the eBPF container monitor here and send out the information. LSMs are not used in that context. Design elements. We started with Kubernetes native engine. It is a Kubernetes native engine today. Most of our deployments are on Kubernetes. We have a Kubernetes operator for system-wide security policies, which basically watches for KubeArmor security policies and then converts it into the native YAML, native LSM specification. We have deliberately chosen, for the reasons specified in the previous few slides, why we had made use of LSMs for policy enforcement and nothing else. In the future, based on the visibility information that we have from CubeArmor, we could essentially derive a SLNX profile, not SLNX, SecCom profile out of it as well. So that is a work. If someone wants to take up that work, we'll very much welcome such kind of contribution, core contributions to this engine. Handling the LSM deployment complexity was one of the things that we kept in mind. And again, in case of cloud providers, we see that cloud providers are in different state of minds. We have GKE supporting AppArmor, we have EKS supporting SLNX. Remember that AppArmor and SLNX cannot work together. They are not stackable LSMs. BPF LSM, which is a new LSM on the horizon, that is a stackable LSM, which means that you can have AppArmor with BPF LSM, or you can have SLNX with BPF LSM, but not SLNX and AppArmor going together. This is another engine that we have recently open sourced, which is, given a generic system here, we get network logs and system logs. We have a flow discovery and system behavior discovery. So essentially, based on the visibility information that we get from Cilium or CubeArmor, we can churn that information and auto-generate policies for you, which means that once you have kept your pods running for a certain duration, you can say, show me all the auto-generated policies, and you'll get a list of auto-generated policies. And then that you can directly apply in the context of your pods. It would be as simple as that. So this is an engine that we have recently open sourced. If anyone is interested, we'd be happy to share the information. I don't know whether the link to the reference is there in this set of slides, but I'll be happy to share that information on CubeArmor Slack channel. Challenges faced, and it certainly does not. We faced a lot of challenges, and I would like to apprise this community and get some feedback, especially folks who have previously worked on SLNX, AppArmor, or LSMs in general. Could be of really great help to the community here. We are facing some challenges with SLNX, which are documented in the link mentioned here. We see BPF LSM as a silver lining because in many cases, we are limited by the policy constructs that are provided by SLNX and AppArmor today. With BPF LSM, that is going to change because essentially we can auto-generate BPF bytecode and push it at a LSM hook and tell the system what to allow, what not to allow. Again, this is in an initial stages right now. This work is in an initial stages. There is a GitHub issue here, issue number 484 on CubeArmor GitHub repo, which has started. We have started doing the initial analysis, and we see that some of the policy constructs are readily supported by BPF LSM, but BPF LSM by itself is not so mature, which means that in context of eBPF, you require BPF helper functions to be available to do something. That ecosystem is not, I would like to say, fully mature today. That's why I don't think today anyone can depend solely on BPF LSM as a for the full application protection. But it would happen for sure in the future years. And so the other problem with BPF LSM is you require kernel version 5.10 and above. Well, we are reaching there, but it will still take few years, and maybe in certain enterprise Linux versions, it may take 5 years to 10 years from now to reach that stage of kernel, and we'll still see some of the virtual machine bare metal hosts still making use of older kernels. So again, all this we want to support with the help of community. There is only limited things that as an organization you can do, but that's why we went ahead saying that this is a problem statement we cannot solve without the community support, supporting all the Kubernetes platforms, supporting all the Linux flavors. In the future, we might have Windows as well. It requires immense thinking. It requires immense design decisions to be taken. All these decisions, if they are not taken out there in open, there are good chances that we might get it wrong. That's the rationale that we had towards going towards a CNCF sandbox project, making this as a CNCF sandbox project. The other aspect is the YAML policy constructs. Today there are set of abstractions that we have created. You can specify, and I'll show you few examples of how those YAML policy constructs look like. But those policy constructs could be extended. Now, in the network world, we already have something called as Kubernetes network policies, right? A primitive which is by default supported for network policies. We don't have something similar for application systems policies. This is a good thing that could be standardized, and I was been told by the CNCF communities that folks attempted this before, but since there was no engine in place, this is the only open source engine which takes LSMs, combines it with Kubernetes, and allows you to do enforcement. So that kind of work in CNCF took a back stage. We believe that with KubeArmor we can reinvigorate that discussion, and looking forward to working with community on that. If anyone has better ideas here, we'll really look forward towards engaging with the community on this aspect. The third aspect is building policy templates for popular Kubernetes world. You have nginx, you have Apache, you have MySQL, Percona MySQL. There's so many pods for which the policy templates could be pre-built. We essentially have started with miters and sticks, and all that is available as policy templates. If you go into KubeArmor as an organization, you'll see a repo called as policy templates. But coming up with an exhaustive list is beyond beyond the capabilities of any one organization. We understood that early on, and that is why we have started building on these policy templates in the open source world. Now, let me reiterate this point that KubeArmor, policy discovery, policy templates, all these aspects are completely out there in open source. Aquinox as an organization is just providing the same thing in enterprise version, whatever is available in the open source version. We don't have anything closed source as of now in this context. Next steps, the primary next step is improving coverage, integrating with BPF-LSM. Like I mentioned, there is already a work happening in the CNCF about standardizing the policy reports. Whatever the alert telemetry metadata that comes out of KubeArmor, those could be standardized. CNCF already has a policy report CRD, and a member from CNCF has already done that, written an adapter for KubeArmor, and it's working well. Building automated policy generation recommendation tools, validating at scale, and essentially taking community feedback on every design decision. Design elements this is something that we'll look forward towards next step. Now, for a demo scenario. Now, this is a demo scenario that I have. We have a WordPress and MySQL application. You can essentially audit the first policy audits all access to this path. If any process does any access in this path, it sends out an alert. We can block any credential accesses by unknown process. For example, this is a configuration file for WordPress, and it contains certain certificate information. So we can allow only WordPress to access this configuration file and deny access to this credential from any other process. Then, the Kubernetes API server block access to the Kubernetes API server. So whenever a pod is started, there is a secrets. If you're using Kubernetes secrets, that secret is mounted at a particular location. And then you want to allow access to that location only for certain processes, and you can do that using KubeArmor, and then block the execution of specific processes. The example that we have is, let me go on to the YAML specification. So these are the sample demo policies for the 4 scenarios that I had mentioned before. This is an action audit, which means any process which is accessing this particular folder recursively, any of the subfolders as well, the action, it spits out a telemetry, an alert with severity 1. Again, this is a user control field. This year, anyone, from if a particular process tries to access this configuration file, then we'll deny it. So remember that this action block results in a deny action. And all the other, so except for one policy, all the other 3 policies are in block mode. Similarly, if someone tries to access the Kubernetes token, we can deny it. This is an easier to understand policy. If excuse me, if anyone is using apt or apt-get within the container to pull dependencies at runtime, the administrator want to block it. That runtime, pulling the binaries at runtime from an external system is a risk. So this could be blocked altogether. In turn, this maps to certain MITRE attack tactics and techniques that are used. So this is the mapping. So before I go into the terminal-based demo, and yeah, we have certain resources and information here. Any questions? I don't know. I've not been observing the chat channel. Nibendra, do we have any questions or of any sort?
You're good, Rahul, for now.
Okay, I think I can directly. Yeah, I can see
go
the
for the
YouTube.
demo.
Yeah. Okay. Fair enough. Fair enough. So we have so what I have here is the KubeArmor running as part of K3s. So we have let me make it bigger. We have KubeArmor running as part of K3s, and I have a sample workload that I mentioned, the WordPress MySQL application here running. So what I'll do is I'll open up a sample. Yes, sample policy. This is a policy which says that I want to block access to apt and apt-get. Okay, so kget ksp -a. We can say that this have alias k to kubectl to k. So this is the Kubernetes security policy, and we can see that it is applied. Now I should be able to exec into the pod, and yeah, you can see that the permission is denied. Right now, let me show you. I can delete the policy, and then exec into the same pod, and then you can see it is working. I mean, this is a very rudimentary explanation, rudimentary demo, but essentially what it shows is you can block processes at runtime. So do we have? So that's the easiest demo. So essentially, this YAML file here is then converted into a AppArmor policy, which is then enforced by KubeArmor. So that is how it is. So essentially, as a user of KubeArmor, you don't have to learn AppArmor, SELinux, or any other LSA. All you need to understand is these declarative YAML Kubernetes constructs, and we are hoping to get these standardized. If just like Kubernetes network policies, we want to standardize systems policies as well, or applications policies as well. And once this is there, then any DevSecOps person or can get this information. Can configure policy without having to learn AppArmor. So that, in a nutshell, is my demo. Let me stop screen sharing and check if I can have.
Yes, one question I have, Rahul, about this. How is it different from the enforcement environment like OPA or Kyverno, right?
Fantastic. Yeah, OPA and Kyverno are admission controllers, right? So what they do is, if a pod is started, they check for a different construct that pod is using. For example, if the pod is starting as a privileged pod, you might not want to allow that, or you might want to send an alert before that privileged pod is started. What KubeArmor does is provide you protection at a much lower level. OPA or Kyverno, they are admission controllers. They don't deal into runtime aspects. So they do deal. But once the pod is found, they don't control that pod anymore. With KubeArmor, you can still specify within that pod only these processes are allowed to be executed.
Correct.
Yeah. And one more thing I want to highlight is, how is KubeArmor using eBPF? Because we got that question when you're presenting your eBPF document, right? So there are two aspects that KubeArmor uses for eBPF. One is the auditing aspect. Once there is an audit event from the kernel clearly does not understand Kubernetes or Docker or containers for that aspect, or for that matter. Once you get an audit event, you need to correlate it with Kubernetes metadata. You want to,
Correct.
you have policy deny, you want to add namespace information, container information, all that. The next version of KubeArmor, the roadmap, as you might have seen for KubeArmor, it integrates with BPF LSM. With BPF LSM, it would be possible to specify eBPF bytecode as policy with LSM hooks, which means there won't be any dependency on SLNX or AppArmor. BPF LSM will do all the tasks with much more flexibility.
Okay, got it. Let's see if there are any comments. So I don't see any. Okay, so thanks, Rahul, for joining us for this session. I definitely learned something new which I did not know about, that you can do LSM with KubeArmor. So I have used AppArmor with the I've used SC Linux and KubeArmor earlier, but consuming them is kind of challenging. Is like, how do I map to the Kubernetes ecosystem there? But I believe definitely with KubeArmor we can achieve that. So that's a good learning for me, and I may use it at some point of time for sure.
Excellent. We are very much looking for contributors. Like I said, there's so many platforms out there. We have VMware Tanzu, so AKS, all these platform support. We are looking for external contributors. If anyone is interested, we'd be happy to. We have a Slack, very active community on Slack. We'd be happy to.
Okay, great. Thank you, Rahul, once again. Just before we sign off, just want to share some more information. Just as we help community to kind of grow. So there is a company called Stowell. They are looking to hire some Kubernetes engineers along with AWS experience. So if anybody in somebody who's watching it, they are looking for some opportunities, you can look at that company and see if you want to apply there. And also, we also have as a Cloudega, we have the our Discord channel. We'll be happy to have you there and discuss more things there. Let's see something on the comments there. There's one more comment here on the chat right now. Let me just put it here. So does KubeArmor uses operator framework underlying?
Yes, indeed. So it does use operator framework, Kubernetes operator framework. In fact, it uses most of the constructs. It has its own. We have our own custom resource definition, as in the demo I showed. Right, there is something called as KubeArmor Security Policy (KSP), and we also have an operator which synchronizes states across multiple pods. Yes, it does use operator framework, Kubernetes operator framework.
Great. Thank you, Rahul, and everybody who is joining the event, maybe watching it now or later. We would be looking for more events like this, and if you want to speak any of the event, please get back. And if you want to hear about any specific topic, that is also perfectly fine. We would be happy to see if we can do it, or we can get somebody from the community to speak on the topic. So perfect. If you want to do any of these things, please let us know. I know that I kind of missed my introduction there in the beginning, but that's okay. So yeah.
I guess everyone knows you, Nipendra.
Not really. Not really. Anyway, I think we'll do it next time, some other time. That's perfectly okay. Okay, so I think we are good for this time. Thanks everyone for joining in. Rahul, again, thanks for you to present a very interesting topic to the community here. We'll see you soon, some other time.
Thank you very much. Pleasure was all mine.
Thank you.
Appreciate it.
Bye-bye. Bye, everyone.